In the previous lecture we started with a review session and we will continue with the review session in this particular lecture as well. The objective of the review session is to revise certain concepts that we have learned throughout this course. So, we were going through certain questions where the objective of the question was to get the answer whether the statement given is true or false. So, we will continue with that. The first question that we will take up today is this question: streamlines and equipotential lines are defined everywhere in a two dimensional incompressible and irrotational flow. The streamlines and equipotential lines are defined everywhere in a two dimensional incompressible and irrotational flow. So, question is, when the streamlines are defined? Streamlines are defined for two dimensional and incompressible flow. Equipotential lines, when they are defined for irrotational flow. So, they are both defined for two dimensional incompressible and irrotational flow. It is perfectly alright. The additional point that I want to discuss is that although they are perfectly defined, but they are not orthogonal to each other at all points. Typically at the stagnation points. Stagnation points are the points where the velocity is 0. So, if you look into the slope of the streamline and equipotential line, the product of that, it is minus of u by v and v by u. So, you go through the derivations of the slopes of the streamline and equipotential line, you will get this. So, when u and v are 0, it is a question of having a 0 by 0 type of form, and then you cannot handle with the situation. Therefore, you cannot discuss about the orthogonality of these two lines at the stagnation point, but otherwise streamlines and equipotential lines are defined. Next question. So, let us refer to the next question. For a two dimensional incompressible and irrotational flow, both stream function and velocity potential satisfy the same governing equation, that is the Laplace equation. Therefore, they are identical. So, for two dimensional incompressible and irrotational flow, both stream function and velocity potential satisfy the Laplace equation. This is correct, this is the Laplace equation. The question is that therefore phi and psi are the same. This is the velocity potential and this is the stream function. The answer is that of course they are not the same, and in fact they are orthogonal to each other. We have discussed about this in one of our lectures. The reason that the governing equations are the same but still the solutions of phi and psi are not the same are the fact that their boundary conditions are different, and that makes them completely different. So, the solution is not identical, that is the question, that is the answer. So, this answer is false. So, we will go to the next question. You have a velocity field v theta equal to c by r, and Vr equal to 0. So, if you have a velocity field of this type where you have v theta as a function of r and Vr identical equal to 0, this is called as a vortex field. So, if you have, so the question is that if you calculate the circulation around a closed contour with the origin or the center included, if you calculate the circulation, then you can clearly spell out that this circulation. So, how do you calculate the circulation? So, circulation along this line, circulation is defined as over the contour, closed contour. So, V theta is in the theta direction and this is in the r direction. So, the dot product of the line element and the V theta along this line is 0 because they are perpendicular, along this line 0, but along this line it is not 0. Therefore, if you consider this contour, then the circulation which we call as gamma is not equal to 0. So, the circulation is non-zero for this contour is true, but the next part of the statement which says that hence the flow is irrotational, that cannot be said, that is not correct. Why? See, if the circulation is a measure of rotationality in the flow. So, normally if the circulation is 0, we say that it is irrotational flow, and if the circulation is non-zero, we say it is rotational. The question is, hence the flow is rotational, not irrotational. So, if you look at the question again, the last sentence of the question, it says that hence, so I am trying to put the pointer here, hence the flow is rotational. So, if circulation is not equal to, if the circulation, so if you now look into the board, if the circulation is not equal to 0, it is supposed to be rotational, but in this case this flow is actually irrotational. So, where is the fallacy? The fallacy is, we have considered the circulation by considering a contour where this point O with r equal to 0 is included, and at that location V theta tends to infinity. So, that is a point of singularity. So, if you are taking a contour to evaluate whether it is rotational flow or irrotational flow, the contour should not contain a point of singularity, and that is the whole problem here. So, it is definitely irrotational flow by choosing another contour which is something like this. Let me make a sketch. So, if you choose a contour like this, you can show that the circulation is indeed 0 around this contour, because this contour does not include this one. So, I have worked it out in one of our lectures. I am not getting into the details. The summary of the concept is very clear, that for calculating the circulation, in order to assess whether the flow is rotational or irrotational, we should not include the point of singularity in the contour. Okay, next question. Next question is little bit elaborate in the statement. So, we will go through the statement carefully before coming into the board to answer it. So, a channel has variable cross sectional area. Consider 2 points 1 and 2 on the along the same streamline within the channel, both points 1 and 2 on the center line, but at different sections. So, if you can write for this A1 V1 is equal to A2 V2, where A1 and A2 are the areas of cross section to which the points 1 and 2 belong, and V1 and V2 are flow velocities at points 1 and 2. So, now let me come to the board and explain the question. So, you have, let us say, a nozzle, just variable cross sectional area. So, I am giving this as an example. So, this is a streamline with points 1 and 2, and the area here is A1, the area here is A2. The velocity at the point 1 is V1, velocity at the point 2 is V2. So, we are claiming that A1 V1 is equal to A2 V2. I think this is the most popular form of the continuity equation in the junior college level. So, question is it valid? First of all, let me discuss about this in length, because here lies the conceptual understanding, and advanced fluid mechanics does not mean always hi-fi calculus or hi-fi mathematics. It is always, I think, emphasizing on advanced or deep conceptual understanding of even basic fluid mechanics. So, this is such an example. So, here you see that first of all nowhere rho appears or density appears. So, one assumption could straight away be the density is constant, but that is trivial, that is very apparent because we are not bringing density into this equation. But even then, is the equation correct? We are writing A1 as area of section 1, but V1 velocity at point 1 that is claimed in the question, and many times for problem solving also we use this V1 for velocity at 1. Actually, if rho is constant, the correct form of this equation is A1 into average velocity at section 1 is same as A2 into average velocity at section 2, assuming that the rho is constant in both sides and gets cancelled. But it is not clearly same as these two velocities are not the same. This is average velocity over section 1, this is local velocity at point 1. But many times for problem solving we use this. So, clearly this is not correct. The answer is this equation is wrong even if rho is constant. But many times we use this equation and we get rid of the error. Why? See, this is very interesting. In practical life sometimes ignorance is a blessing in disguise. So, how this ignorance can be a blessing in disguise? In many practical situations in fluid mechanics the flow is turbulent, and if it is turbulent the velocity variation, the velocity profile is more or less uniform. Then if the velocity profile is uniform or very close to uniform, why in turbulent flow the velocity profile is more or less uniform? It is because of rigorous mixing across various fluid layers that the flow profile, the velocity profile tends to get uniform. So, if the velocity profile tends to get uniform, then what happens? Then the local velocity and average velocity, they are not any way different. So, this can be used provided that the velocity at point 1 is roughly the same as the average velocity over the section 1, and that is there if the velocity profile is uniform. So, with those additional assumptions only you can use A1 V1 equal to A2 V2, where V1 and V2 are the velocities at the points 1 and 2. So, in general not, therefore, this statement is false. Okay. So, we will take up the next question. If you look into the screen, for an unsteady flow, so let us look into the screen. For an unsteady flow, the continuity equation, the general continuity equation is not valid if the flow is viscous. So, this is a straightforward question. So, the claim is that this equation is not valid if the flow is viscous. So, this is clearly irrelevant and false. The reason is that this equation is based on conservation of mass. Now, conservation of mass does not care whether it is viscous flow or inviscid flow. Okay. So, it has nothing to do with the flow as viscous or not. Okay. The next question is if the continuity equation for a flow field is given by divergence of velocity equal to 0, then the flow may be unsteady. So, this equation can you tell that whether you can get an idea of whether the flow is steady or unsteady from this equation? Clearly the answer is you cannot. The reason is that this is a purely kinematic equation. So, this just talks about incompressible flow, not about the steadiness or unsteadiness. So, the illusion that is created is you think that del rho del t term in the continuity equation is not there, and therefore this equation is arrived at. I will show you that even if del rho del t is non-zero or any other property or velocity varies with time, you can still arrive at this equation. So, how it is possible? So, you have, so the general continuity equation, let us write that in Cartesian system. I will write the Cartesian system because it will help you to assimilate the concept. So, let us write I am using the product rule for derivative. Okay. So, now if you take this part 0, then this is equal to 0, but that does not mean that del rho del t equal to 0. In fact, that means that this total term, which is the total derivative of rho with respect to t, this is 0. So, the first part of the answer or the first part of the question is pretty straightforward. If this is 0, the flow may be unsteady, the answer is correct. But I want to discuss a little bit beyond that, that we have an idea in mind that for incompressible flow the density is constant. May not be the case, because for incompressible flow this term is 0, that means that the remaining sum of the terms is 0, but that does not mean that rho is a constant. It may so happen that this term and some of these terms combined together make the total derivative of density equal to 0. So, such a flow is called as variable density incompressible flow. So, we understand two important concepts through this question. One is from the question itself, from the answer to the question itself, that this does not imply that the flow has to be steady, and the second is that when this is 0, that does not imply that density has to be a constant. So, density can be a variable and still it is incompressible flow, that is called as variable density incompressible flow. The incompressible flow terminology does not come from density constant or density variable, It comes from the kinematic constraint that volume element of the fluid of the chosen volume element chosen in the fluid, that volume element does not change in volume. So, it is a kinematic condition that the volume does not change, instead of considering density, which is a fluid property. The next question: along the direction of a steady inviscid flow, if the cross sectional area of the flow decreases, then the pressure must necessarily increase, assuming that it is a horizontal, the flow is taking place along the horizontal. So, gravity effect is not coming. So, the example is like the cross sectional area is decreasing. So, expectation is pressure is increasing. So, where from this expectation is coming? So, here you have area A1, here you have velocity V1, sorry, area A2, here you have average velocity V1, here you have average velocity V2. So, the idea is that if the area decreases, the velocity will, this is the common idea, I am not saying it is correct. The common idea is that because the area is decreasing, the velocity is increasing, and because the velocity is increasing, from the Bernoulli's equation the pressure is decreasing. If the velocity is increasing, because the area is decreasing, the velocity is increasing, and if the velocity is increasing, the pressure is decreasing. Now, that type of idea, very simple idea, does not hold if the density variation is playing a very interesting role. The reason is that when you say that area is decreasing, therefore the average velocity must be increasing, that is true only for incompressible flow. But if the density variation plays its role, then of course you cannot really make such a conclusion. And then, so the answer to this question is whether the pressure will increase or decrease or whatever, it depends on the nature of the flow. You cannot really predict it just from the information that the velocity or is in the, sorry, the cross sectional area is decreasing. So, necessarily, see this statement in the question, the pressure must necessarily increase or decrease of whatever, necessarily you cannot say, it may increase, may decrease, it depends on how the density is varying. Okay. So, let us get on to the next question. Bernoulli's equation can be applied along the center line of a pipe in fully developed flow, since the shear stress is 0 at the center line. So, fully developed flow will have a velocity profile in pipe something like this. So, here the velocity gradient is 0, that means the locally the shear stress is 0, and because the locally the shear stress is 0, the claim is that the Bernoulli's equation can be applied along the center line. The answer is not that it is not correct. The reason is that Bernoulli's equation is valid for inviscid flow, right, but here the fully developed flow means that the viscous effect has penetrated even to the center line of the pipe. So, clearly viscous effect is there. Next question: in a pipeline transporting fluid with negligible viscosity, fluid always flows from higher pressure to lower pressure. Okay. So, this is a very common idea that we have, that fluid will flow from always high pressure to low pressure. Let us just look into an example, some arbitrary example. So, let us say this is an example where fluid is flowing in this direction. So, the parameters, so if you are dealing with inviscid flow, you can deal with parameters pressure, velocity and height. So, if you have a high pressure which is so if you have this type of cross section, the average velocity here and average velocity here, which will be more? The average velocity here will be more or less, the average velocity here will be more if rho is constant. So, if the average velocity is more, the height is also more, so pressure will be less even if the fluid is flowing from here to here. Okay. One big question comes that just some time back I told that it is not the local velocity, but it is the average velocity that we are talking about. So, can we write the Bernoulli type of equation with the average velocity instead of the local velocity? Yes, we can do that, and let me write that equation. This elusively looks like Bernoulli's equation, but this is not the Bernoulli's equation. So, I will explain you the terms. So, this looks like Bernoulli's equation, but this is actually a mechanical energy conservation equation. This alpha is called as a kinetic energy correction factor, with an understanding that the average velocity does not represent the kinetic energy. So, the kinetic energy is based on the variable velocity, but not the average velocity. So, a correction factor is included. So, this is flow energy, this is kinetic energy, this is potential energy. At 1, this is the sum of the energies at 2. The difference is because of the fact that energy at 1 is always greater than energy at 2 if there is no heat transfer. This is heat transfer, Q dot Cv is positive if there is any heat transfer to the system, if it is negative if there is any heat transfer from the system. So, in an adiabatic flow, this is 0 for adiabatic flow, we are not considering heat transfer in this particular course. This I2 minus I1 is a change in internal energy, increase in internal energy, and this occurs because of viscous action. So, we can say, so this is the head loss due to fluid friction, so to say. So, because of viscous dissipation in the fluid, actually the fluid gets heated up and its internal energy increases. So, we can clearly see that if this has to be positive, and therefore, if you consider this term and this term, this is greater. So, if now this term is greater than this term and this term is greater than this term, you will still have P1 less than P2, but the flow is still flowing, fluid is still flowing. So, fluid flowing from high pressure to low pressure is a very special case, but to generalize it is a myth. The generalization is fluid will always flow from higher energy to lower energy by virtue of the energy gradient, and that need not necessarily be provided through pressure. It could be provided through kinetic energy, potential energy, or any other form of driving force. Okay, let us take maybe a couple of additional questions before we call it a day for this particular session, but I will provide you with the remaining questions through our portal so that you can work on the remaining questions. So, the next question, if you see, the following form of momentum conservation equation is not applicable for compressible flows since density is taken out of the derivative in the left hand side. So, to answer this question in a very short way, this particular density which is coming out of the left hand side of the momentum equation, which is called the non-conservative form, this density does not come out because it is a constant. This density comes out because of manipulating the conservative form of the momentum equation with the help of continuity equation. So, with simplification using the continuity equation, the rho comes out. So, elusively this rho out of the derivative does not mean it has to be a constant, it could still be a variable. Okay. The next question, a Newtonian fluid need not necessarily be Stokesian for satisfying the incompressible form of the Navier-Stokes equation. So, Newtonian fluid we have already discussed. What is the Stokesian fluid? The Stokesian fluid is for which 3 lambda plus 2 mu equal to 0, where lambda is the volumetric dilation coefficient. This is the definition of Stokesian fluid. We have discussed about this. So, you will see that in the derivation of the Navier-Stokes equation, this comes with the divergence of the velocity, product is important. So, even if this is 0 or non-zero, whatever it is, we do not care if it is incompressible flow. Of course, it will be satisfied, the Stokes hypothesis will be satisfied, but even if the Stokes hypothesis is not satisfied, the thing is we will not care, because if this is 0, the product of these two will be 0. So, whether lambda is minus 2/3 mu or not really does not matter. So, for an incompressible flow, even if the fluid is non-Stokesian, still you will get the same version of the Navier-Stokes equation that we get for the Stokesian fluid. We will take a couple of more questions which are there in the screen. Viscosity of gases usually increases with increase in temperature, whereas the reverse behavior is expected for liquids. So, viscosity of gas will increase with increase in temperature, because for gas the viscosity is primarily attributed to the transfer of molecular momentum across layers. So, if you have higher temperature, there will be more vigorous momentum exchange. So, what momentum exchange does is it tries to slow down which is faster, and it is try to accelerate which is slower. So, this momentum exchange actually contributes to the viscosity in gases. Higher temperature means more vigorous momentum exchange. For liquids, viscosity is primarily due to intermolecular force of attraction. So, higher temperature means molecules will usually have a tendency to go further apart, so the intermolecular attraction will decrease and the viscosity will decrease. The final question that we take up today is, there is no work done by the fluid to overcome frictional resistance offered by a pipe at the walls. So, this appears to be a very disturbing statement. We see that so much of energy loss for flowing through a pipe with friction, but the question claims that there is no work done by the fluid to overcome frictional resistance offered by the pipe at the walls, and actually this statement is correct. Why there is no work done at the walls? So, the key is that in the question there is a phrase at the walls. So, why there is no work done at the walls? The simple reason is the work done, also the rate of work done depends on the velocity, and because of no slip boundary condition at the wall, the relative velocity between the fluid and the solid is 0. So, although there is frictional force, there is no work done or no rate of work done to overcome it at the wall, because the velocity, relative velocity between the fluid and the wall is 0. So, the question is then where from this dissipation comes, so that you need to supply energy to the fluid to flow in a pipe. The dissipation comes from actually the work done to overcome frictional resistances between various fluid layers, where there is a relative velocity, but not at the wall. So, we have come to the end of the review session. We have discussed some questions. I hope these questions have been very interesting and stimulating for your mind, and I hope some of your doubts have been clarified. We will supply you with more questions, and please feel free to interact with either me or my teaching assistants, and all the best for the remaining part of this course and your exams. Thank you very much.